spent some time thinking about degree 2 polynomials. And at this point, like, any question I ask you that's about a degree 2 polynomial, you can answer. Partly because completing the square lets you graph it. So as soon as you can graph something by hand, you can answer any question. You want to find the x-intercepts? You have a quadratic formula. That quadratic formula comes from completing the square. High degree polynomials are hard art in that some of these tools just don't exist. But you can still do lots of things with them, and maybe a good place to begin is with just an example of where you might encounter a polynomial degree bigger than 2 in the wild. So here's a made-up example, but hopefully one that'll seem motivated enough. So you start with a 2x3 sheet of cardboard. I guess that side seems longer. 3x2 sheet of cardboard. You're going to make a little square cut in each of the corners. So cut out a little corner from each one. And the reason you'll do that is because you want to make a box. So you're going to take that and fold it up. What is the volume of the resulting box? And a lot of people start with this. What's the formula of the volume of the box? Length times width times height. So if we can figure out the length, width, and height of the resulting box, then we'll have an answer. So maybe it's worth drawing a picture. So I'm going to make these cuts. I'm going to fold along these edges. Maybe some color coding will help. So as a consequence, that'll be the bottom of the box. So you'll see this bottom of the box appearing here. And then these sides that I've drawn in purple will be the height of the box. Whenever you're doing something that's geometrical in nature, even if the picture doesn't wind up being good, I think this one turned out okay. It's useful to draw the picture. All right, so length, width, and height of this box. What will they wind up being? I think the height's the easiest to see. That's just x. Right, this little bit that you fold in was an x by x cut. The height is this parameter x. So if you like, it's an x because it's something that I'm going to choose. I'm going to decide how big a cut I want to make in this box. How long is the base of this box? I hear 3 minus 2x. Why 3 minus 2x?
Because we roll length, the original thing is 3, and we take out 2 of the squares, which are x.
Yeah, cool. People agree? I think I agree. X by 3 minus 2x. I guess that means you also know what the other side length is going to be. 2 minus 2x. All right. That enough to determine the volume? Yeah, I think so. Volume, V for volume, it depends on x, is x multiplied by 3 minus 2x times 2 minus 2x. And maybe we'll also, this is actually modeling something that's supposed to be a real wall or something. So what constraints are there on x? What numbers don't make sense? Yeah, just say that. Negative or 0. 0 is an edge case, whether it makes sense. 0 would just be do nothing. So maybe you don't count that as a box. So I don't know. Include or exclude endpoints is depending on, well, you said to exclude, so I'll exclude 0. That's a technical reason why sometimes you want to include those endpoints. But it doesn't matter. Could you make an arbitrarily big cut here? Could I cut a 500 by 500 square out of each corner? Yeah, that would be more than the box. What's the biggest cut you could make? I think 3 is a little bit too big. That would be like, from here I'm going to cut out something bigger than the whole box at each corner. I wouldn't have anything left. 1.4. All right. I think that's still a little bit too big. Remember, this height's only 2. So that would be making a cut that's like that big at each corner. Should the cuts be able to overlap? I think that's a bit much. So what's the biggest you can get those cuts to be without having them overlap at all? Slightly less than 1. So maybe just up to 1, but excluding 1. And again, whether or not you want to include or exclude, I guess if you cut it all the way to 1, they'll meet, and then you'll, like, not quite have a box. Maybe there's nothing left to fold. I think you just fold the whole box in half. So it looks like the domain of this is just from 0 to 1. It's a degree 3 polynomial, so maybe I'd ask you to optimize this. We don't have good tools to optimize degree 3 polynomials, but we have a reasonable tool to optimize, like, anything. What's one thing we could do to decide what the maximum value we can make is? If we're okay with estimating. And we're allowed to use a computer. Yeah, we could graph this thing. We could look at a graph and just say, oh, maybe there's an obvious peak in between 0 and 1. So let's try to do that. Let's pull this up. Do want those other graphs in a minute. Let's graph. X times 3 minus 2x times 2 minus 2x. And you know what? I want to graph it just from 0 to 1. I'll go a little bit past. Just there. Cool. That looks like now a reasonable picture of this thing. So between 0 and 1, does it look like it has a maximum value? Yeah. About what does the maximum value look like? There. Maybe now it's easier to get more digits. Somewhere around 1.06-ish is the maximum value. And it corresponds to a particular x value. About what x value produces that x? Say louder. For the x value? 0.4-ish. And I don't think there were any units specified in the problem, so that's the best we can do. So that's not even something special about polynomials. You can just always do that. Do you think that, like, exactly 0.4 is the right answer for the x value that optimizes? No. We, in this class, won't actually develop reasonable tools to find that x value on the nose. As a sales pitch, you will when you take Calc 1. Because, well, in Calc 1, you want to find those turning points. I guess Desmos is giving us more digits because it knows that that max is probably important. You know. All right, so polynomials. What is a polynomial? And let's start with degree 2, because that's something we know. A degree 2 polynomial is just a quadratic function. And the quad there is just quad plus square. Degree 2 is because we'll see that 2 is the biggest thing. What's a quadratic function? What's a degree 2 polynomial? Anything that's a square term plus a linear term plus a constant term? It's anything that looks like ax squared plus bx. plus c. So I don't know, like 3x squared minus 2x plus pi. There's a degree 2 polynomial. And from there, let's go up. If that's a degree 2 polynomial, then what should a degree 1 polynomial be? Yeah, I think you said like x plus 5 plus, or at least that's what they found from somewhere, I don't know. Yeah, any ax plus b. Maybe you like mx plus b, because that's the letter we used for the slope earlier. A linear function is a degree 1 polynomial. So what should a degree 0 polynomial be? Just a constant. So 5 is a degree 0 polynomial. There's an edge case that isn't important for this class. I'm going to put this in the side just for the sake of completeness. Sometimes you'll hear someone saying that just the function y equals 0 is degree negative infinity, which is a weird thing to say, but some things work out correctly if you make that assumption. That's not something that will be important to us. Degree 3 polynomial. So if a degree 2 polynomial is something like ax squared plus bx plus c, then what's a degree 3 polynomial? Same thing, but it'll go up to degree 3. Just something like that where a, b, c, and d are constants. What about a degree 4 polynomial? Same thing, but up to the 4th. In general, then what do I mean by a polynomial? So there's a degree 4 polynomial. Could you also say what a degree 5 polynomial is? Degree 6? Do you think you could just say what I mean by polynomial in general then? What do I mean? What's a polynomial? Tell me in words.
What the x part is like.
Oh, sure, that's like what the degree is like how high sure. But that means you have some idea what goes in the previous line. Right? If you have a polynomial, its degree is like what's the biggest power you see on x. So I guess that means a polynomial is some powers, yeah. Yeah. I'll mostly be interested in one variable polynomials in this class. In fact, I'll only be interested in one variable polynomials. You can't have like polynomials in multiple variables. It is, I'll write it this way, a sum of multiples of powers of some independent variable x. Does that agree with what's in the previous lines? Each of those previous lines are like sums? Are each of the things in the sum a multiple of a power of x? And maybe we'll even want to be picky about what powers. Let's demand that they be like whole number powers of x. So I'm not going to allow like x to the negative fifth in a polynomial. I just won't call that a polynomial. Some people would give it a fancy name. That would give you a class of things called Laurent polynomials, which are polynomials. Cool. 1 plus square roots x, so no fractional powers. Feel okay about that definition? Maybe we'll just do a quick test out. So I said this was a polynomial. Is that written right now as a sum of powers of x? No. But could we write it as a sum of powers of x? Yeah, maybe we'll even do that. This thing has phi of x equals, so I guess I have to like do a bunch of distributing. And maybe I'll start by just FOILing out this part. X times 3 times 2 is 6. 3 times 2 is 6, so minus 6x minus 4x plus 4x squared. Oh, now we see some powers of x showing up. And maybe I'll try to do 2 things in one step. There's some simplification, right? What's minus 6x minus 4x? Negative 10x. Let's replace that with negative 10x. And I guess I also have to distribute this x through. 6x minus 10x squared plus 4x cubed. Oh, cool. Is it degree 3? Is that what we said it should be? Nice. In fact, do you think you could have recognized that this is degree 3 without doing that hard work? Yeah. Like that's degree 1, that's degree 1, that's degree 1. Degree is going to add when you multiply. Nice. So, let's go to the next page and just do some recognition of things just to see if we internalize that definition. Which of these 6 functions is a polynomial? Are polynomials. Multiple of these will be polynomials. What is the degree of the things that you call polynomials? So, take a moment, stare at each of those for a second. Maybe discuss with those around you. We will come together and ask. Cool, let's see. 5. Is that a polynomial? Folks for yes? Folks for no? Cool. Those of you who said yes, what's its degree? Degree 0 polynomial. Constants are polynomials on a technicality. They're degree 0 polynomials. They also happen to be constant functions, so if you're studying a degree 0 polynomial, you probably should be treating it like a special function that's just constant, and not like a generic polynomial. So, technically it's a polynomial, but you want to think of it as special. 1 over x, is that a polynomial? Folks for yes? Folks for no? Cool, why not? Polynomial is supposed to be like positive powers of x added together. That's a negative power of x. This is not a polynomial. Next one, 4x to the 5th minus x to the 4th plus 3x plus 2. Is that a polynomial? Cool. Those of you saying yes, what is its degree? 5. Because of this 5. X plus 1 over x minus 1. Is that a polynomial? Folks for yes? Folks for no? Why not? Yeah, you're not allowed to divide by x's in a polynomial. This is an example of another type of function which we will study called a rational function. It's not a polynomial. Next one, x plus 3 times x plus 2 times x plus 1. Is it a polynomial? Folks, but yes. What's its degree? 3. And you can see that it's degree 3 without actually FOILing it all out, which would not be impossible, but would take some effort. If you waterfoil it out, that would contribute an x, that would contribute an x, that would contribute an x. The biggest power you would see is x cubed. Final one, 2 to the power of x. Is it a polynomial? Anyone want to say yes? Anyone want to say no? It is another example of something that's in a bigger class of functions that we'll call exponential functions. You can't write that down as any just finite sum of powers of x. Right, because you're not allowed to see an x and an exponent in a polynomial. X can be the base of an exponent. But you're allowed to raise x to a power, not a power of 2x. Gesundheit. Not a polynomial. It's an example of something that we will call exponential. Cool. Feel all right? So, what I'd like to start doing is Gesundheit. Getting some intuition about what the graph of a polynomial will look like. And maybe just forced to see that they can be more complicated than degree 2 polynomials. Because, right, like basically every degree 2 Gesundheit polynomial looks the same. It's all a parabola. Maybe it's flipped, maybe it's stretched, and then it's shifted around. Here are some degree 3 polynomials, and they'll look fundamentally different. Here's just the graph of y equals x cubed. And let's just answer some questions. How many roots does it have? Sorry, root is code for how many places are there where this thing is equal to 0. One root at x equals 0. How many turning points does it have? How many places are there where it changes from Gesundheit, increasing to decreasing? Kind of. It's got one place where it like flattens out. But does it actually go from increasing to decreasing at that point? So by like the technical definition we gave, this is not a turning point. It has no turning points. If you want the answer to that question to be 1, then like a buzzword that we haven't used in this class is a place where the graph evens out, where it flattens out. It's called a critical point, regardless of whether or not it turns around. So every turning point will be a critical point. Not every critical point is a turning point. Critical point is not a law that I've defined in this class. The next one is x times 2x squared plus 1. Let's ask the same questions. How many roots? 1. How many turning points? Also none. It goes from increasing to still increasing. In fact, what if I want to ask you how many critical points there are? How many places are there where it like flattens out? You sure? Look at x equals 0. What does the slope look like at x equals 0? It might be fair to like pull up a computer and play the zooming in game. So there's the graph of x times 2x squared plus 1. Let's zoom in really close to 0. What would you say the slope of that looks like when you zoom in real close? Looks like y equals x. This looks like slope 1. Is that a turning point? Is it a critical point if a critical point is a place where it flattens out? Nope. It doesn't even have critical points. So this is fundamentally different behavior than y equals x cubed. Or maybe we'll just indicate this 1 root. How many turning points are there? There are none. There aren't even any critical points. Feel pretty okay? Nice. Let's go back to a standard zoom. All right, next one. X times x, 1 minus 1/3 x times x plus 1. How many roots are there? There are 3 roots, and we could even list them. It looks like one of them is at x equals -1, one of them is at 0, one of them is at x equals 3. Looking close at that, how many turning points does it look like there are? there are two, it looks like. And finally, x times x minus 1 quantity squared. Same question. And that picture is a little bit hard to read, so let's pull it up here and get a more reasonable viewing window. How many x-intercepts? 2. How many turning points? Also 2. So it looks like you could have 1, 2, or 3 roots to a degree 3 polynomial. You could have up to 2 turning points, it looks like. And that's all good information. I'll put that down here. A degree d polynomial will have at most d x-intercepts. And maybe I'll put a thing in parentheses. This will be exactly d if you count with multiplicity. And what do I mean by that? I mean that, like, this point right here, where it came down and bounced off, count that as 2 roots at the same time. It's like multiplicity 2, because it comes from a square root. So if you're willing to do that, there will be exactly d roots, with one added caveat. Is that even true for degree 2 polynomials? Does every degree 2 polynomial have exactly 2 x-intercepts? Yes-ish. If you're willing to count with multiplicity, so when it just bounces off the x-intercept, that counts. And you have to be willing to count complex solutions. That's right. Every degree 2 polynomial has those 2 complex roots. So if you're willing to count with multiplicity and allow complex roots. It's hard to find them sometimes, but they exist. Any degree d polynomial will have at most d minus 1 turning points. And the next thing I want to point out is something that will be like really simple behavior on the part of polynomials. Exactly how those roots and x-intercepts can interact can be super complicated. But there's one behavior that polynomials have, which is really simple. So here are the graphs of the same 3 polynomials. X cubed, x times 2x squared plus 1, x times 1 minus 1 third x times x minus 1, and x times x minus 1 squared. But I've zoomed out quite a bit. X is now running, no, not even that much, from negative 10 to 10. The y values are running from negative 2,000 to 2,000. So tell me about how those graphs compare. Do they look similar to each other somehow? In fact, let's maybe say this. So from this first graph to the second graph, what has changed? How does one relate to the next?
The second one's steeper.
It's steeper. The y values have been stretched. Here it looks like the y values have been multiplied by 2. So it sure looks like this is basically the same as 2x squared at this scale. And maybe we'll even check that. Oh, cubed, not squared. Pull up the same Desmos graph. There's x cubed. There's x times 2x squared plus 1. Maybe we'll add in there 2 times x cubed. Does that line up pretty good with the blue graph? Yeah. The next one in the list is, well, here it is expanded out. 1 third x cubed plus 2 thirds x squared plus x. How does it look like x cubed compares with that? been flattened? Any guesses for, like, what factor it's been flattened by? Let's just try one. Right, we have this computer tool pulled up. Maybe I'll try 1/2. Need to see it. So, let's see. The purple graph, the red graph's just in the way. I want to turn that purple graph into the blue graph. What things do I need to change? I think a flip is in order. Let's flip it over the y-axis. How do you flip a thing over the y-axis? Just multiply, you stick an extra negative sign up front. All right, do they line up exactly yet? So I think I want to divide the blue one by something a little bit bigger. Give me something a little bit bigger than 2 to divide by. How about 3? 3 is a little bit bigger than 2. Dumb luck. That look a little closer? In fact, I think I want to get to the point of saying that they're really close by zooming out further. At this zoom, do they really look like they line up pretty good? Yeah. So what we see here, and maybe for emphasis, I'll circle this piece, is that's really close to -1/3 x cubed. What about the next one? How does it compare with just x cubed? Oh, and this should be an x cubed, shouldn't it? This is basically just x cubed. So here's the observation. Once we FOILed out, these leading terms just controlled all of the behavior. If we take a degree d polynomial, there it is, d term times x to the d plus some lower order terms, and you zoom out sufficiently, the graph will just look like the d term times x to the d, and maybe just to see if you've internalized that. So if you zoom out a bunch on that degree 7 polynomial, what should it wind up looking like? It'll just be the leading term. When you zoom out a lot on a polynomial, all you see is the leading term. That feel okay? Nice. So let's put some of this stuff together. So let's go the other way. Let's suppose you saw this graph. Tell me, how many roots does this thing have? Just one? So that doesn't tell me much. If I only know this fact, I guess that tells me that the degree of this polynomial is bigger than or equal to 1. How many turning points does it have? 2. And I'm going to flash back to the previous page. Any degree d polynomial has at least d minus 1 turning points. So that tells me for this next polynomial, d minus 1 has to be at least 2. So the degree minus 1 has to be at least 2. So what's the least the degree could be? 3, I guess? That's good information. Say again? Yeah, let's. So any degree d polynomial has at most d minus 1 Turing points. So that means d minus 1 is bigger than or equal to the number of Turing points. Right, that's just what, how to write at most as an inequality. All right, so that gives me more information. That tells me the degree of this polynomial is at least 3. And let's also ask about asymptotic behavior. So it's hard to take this static picture and zoom out. But if we did zoom out, we'd lose all of that information that happens at the middle. We just see the end arrows. If you only saw that much of this graph, what degree would you say that looks like it might be? Does it look like it has even degree? Does it look like an even power function? It looks like an odd power function anyway. And I guess it's hard to be sure beyond that, right? Like maybe it's just a super steep degree 1 at this scale. But the degree is definitely odd. And maybe one more question. So it's going to be an odd power function. Does this look like x cubed or negative x cubed? X cubed. It's not like flipped over the x-axis. So this will be, so what conclusion can I make from this? This is a polynomial. Its degree is at least 3. Its degree is odd. And I think the leading coefficient is positive. I think those are the things we can tell just by looking at this graph. That feel pretty okay? So you can tell a lot of things about a polynomial by looking at a graph. And you can detect, for example, its degree. At least you can get control bounds on the degree. You can tell if it'll be an even or odd total degree by checking the asymptotic behavior, and you can even figure out the leading coefficient. Let's flash back to x times x minus 1 squared for this next example. So what I want to start building is the idea of if you see a polynomial that's factored, it'll be easy to graph. And this is an example. This polynomial is totally factored, right? It's just a bunch of linear things multiplied together. Let's try to figure out what that means about the graph, and let's start by looking at, I'll copy down a computer-generated graph. The graph looks something like this. Now the two roots you see to this polynomial, at 0, 0, and at 1, 0, like, those two roots look fundamentally different, right? If I zoom in really close on 0, 0, what would you say that looks like? Like a straight line? Maybe you'd even say the slope looks like 1. Saying the slope is 1, that's exactly the purview of calculus. Calculus lets you compute the slope of a curve at any point. By eyeballing it, this looks like it has slope 1. So let's see, near x equals 0, the graph looks like a curve with slope 1. Oh, you couldn't see what I drew. I didn't draw much. Let's also think about what happens near x equals 1. And let's do that by just shifting the viewing axis to center on 1. And I think, okay. There we go. That'll do. Let's stretch out the y values a little bit. There we go. What would you say that graph looks like? Parabola? Near x equals 1, it sure looks like I see a parabola. So the point is that this isn't special about this polynomial. This always happens whenever you have a polynomial in factor form. Oh, well. That's not where those pictures were supposed to go. That's okay. So the point is, as soon as a polynomial is factored, you can read off the graph. So I'll write something very formal and technical looking, and then I'll put it into plain words right after. If a polynomial factors as p of x equals q of x, so q of x is another polynomial, times x minus c, so a linear polynomial raised to the power p, with q not equal to 0 at c, then when you look close to x equals c, the graph of p will look like q of c times x minus c to that power. So let's just say what this means slightly less formally. To sketch a graph near a root, and let's say that root is at x equals c. What can you do? You can plug x equals c into all of the factors of the polynomial which don't contribute to there being a root. And then for all the rest of the factors, well, you have to remember them because you actually want to study the root. So whenever you want to sketch a graph near a root, let's say that root is at x equals c. So c is the location of the root. Plug that x value in for all of the x's that don't have to do with the fact that there's a root. And then, well, you have to remember the ones that actually contributed to the root. I think that it will help to make this explicit by using this idea to sketch a graph by hand. And then once we have this graph sketched by hand, we can compare it with the computer-generated graph. So that's the last thing I want to do today. Let's sketch the graph with some polynomials. Seem reasonable? Cool. Let's do it. So here is a polynomial. Is it already factored? Yep. In general, factoring a high-degree polynomial is hard. As in, like, provably hard. You can't teach a computer to do it exactly. Sometimes you can't conclude that you cannot do it by using purely algebraic stuff. So factoring can be hard, but if you've already factored, you don't need to. So let's, step one, can you tell me where are the roots of this polynomial by looking at this expression? Well, maybe we'll start with that. Let's find the zeros. X times x plus 1 squared times x minus 2 cubed equals 0. 0 is a special number, in that the only way you can multiply things together to get 0 is one of them has to be 0. So I can split that into 3 separate equations. Either x equals 0, x plus 1 equals 0, or x minus 2 equals 0. Right, if all of them were non-zero, if they were like 6, 7, and 5, then the product wouldn't be 0. Each of those look easy to solve. So if x is equal to 0, then what is x? Yeah, that's a stupid question. If x is equal 0, then x equals 0. So you know that 0, 0 is a root. 0, 0 is an x-intercept. X equals 0, 0. X plus 1 equals 0. What is x in that case? Negative 1. X minus 2 equals 0. X equals 2. All right, neato. So, for near each of those roots, the polynomial will basically look like a stretched or shifted polynomial. To see that, we'll use the trick that we developed on the previous page. If I want to graph near x equals 0, I have to remember the factor that resulted in that root. Which of the factors up there resulted in the root of 0? Yes. When you plug in 0, this piece is 0. Plug in 0, this piece is 1. So it doesn't contribute to the root. Plug in 0, this piece is minus 2 cubed, I guess. So, near x equals 0, I need to remember this piece. And then I can plug in x equals 0 for all of the other x's. And let's see how that graph looks. So I guess we need to actually evaluate those. So that'll be x times, what's 1 squared? What's negative 2 cubed? Negative 8. So it'll be x times negative 8. So that'll be like a negative slope near 0. And maybe it'll be like pretty steep. But I'm not trying to get like a perfect scale. I want a cartoon picture. Near x equals negative 1. Play the same game. X plus 1 squared is the piece that contributes to the root. Plug in 1 for all the rest of the x's. Negative 1 for all the rest of the x's. So, that'll be x minus 1 squared times a number. That number will be negative 1 times negative 3 cubed. I think that works out to be 27. But the most important thing is that it's a positive number times that degree 2 thing. So close to x equals negative 1, I should see an upward opening parabola. Wouldn't it be negative 27? Why negative? So it'll be negative 1 times this x plus 1 squared needs to stay, times negative 3 times negative 3 times negative 3. So I see 1 negative, 2 negative, 3 negatives, 4 negatives. I think maybe you lost this first one. Okay. And then play the same game at the other root. Near x equals 2, plug in x equals 2 for all the factors other than the x minus 2 cubed. So this will be x minus 2 cubed. 2 times 3 squared. Is that 18? I think it's 18. But I don't think I actually care that it's 18. It's a positive times x minus 2 cubed. So close to x equals 2, I should see something that looks like x cubed. And what will I do from there? I will interpolate between. All right, so now let's try to say what happens when x is big. So this is like the zooming out thing. What's the total degree of this polynomial? Degree 6. If you want to FOIL it out, the leading coefficient would be 1. So, for a big x value, this will be basically x to the power 6. And I know what x to the 6 looks like. It does that. So there I've drawn a by-hand cartoon graph of what this graph will look like. And as you pack up, maybe I'll do one thing to do a sanity check. Could I also have a computer graph this? Nope, nope, not that button. This one. Let's graph x times x plus 1 times x minus 2. This one should be cubed, and I lost the squared. How did we do? Was that pretty close to what we graphed? Right, I wasn't trying to record the right height on that keyboard. And I am out of time.